is a decentralized protocol which enables cow swaps using Uniswap v4 and EigenLayer. It's an actively validated service to enable coincidence of wants matching on any Uniswap v4 pool through v4 hooks. Operators of the AVS run an optimization algorithm to find the best possible matching for users, enabling them to swap at the best possible prices. It is economically secured by EigenLayer. It finds cow matching between any n number of swaps to offer the best prices to the users. It is general purpose and can support any v4 pool. It falls back to using the v4 AMM for liquidity if a better price through cow cannot be found. The simplest case of cow occurs when two exact and opposite trades are found. In an ETH USDC pool, for example, if the spot price for ETH is 3000 USDC and Alice wants to sell 1 ETH, whereas Bob wants to sell 3000 USDC, Alice and Bob can be matched with each other, trading 1 ETH versus 3000 USDC, enabling both of them to get a better price than the AMM. Another example of cow occurs when more than two trades are found that can be cow matched together. Alice wants to sell 1 ETH, Bob wants to sell 2000 USDC, Charlie wants to sell 700 USDC, Darcy wants to sell 300 USDC. Alice's trade can be matched against Bob, Charlie, and Darcy's trade, enabling all of them to get a better price than the AMM. Now let's talk about the user flow. User will send a swap with hook data indicating that cow is enabled. It will go through our UniCow hook, which will do a no-op and take custody of all the input tokens. It would further create a task by calling the create task function on our UniCow service manager, which will emit a create task event. Operators will actively listen to this create task event and add them to batches. Once a batch is completed, a cow algorithm would be run, which would return the best possible combination of tasks. Operator would further respond to tasks and call settle balances on our UniCow hook.sol. Why EigenLayer? EigenLayer helps to decentralize the protocol. UniCow protocol will not be restricted to one algorithm. It is more gas efficient to do the cow off-chain and then settle balances on-chain. Finding optimal matchings for cow is an NP hard problem. That is, there is no way to solve for the optimal matching. For the hookathon, one implementation of a matching algorithm has been done, which brute forces all possible solutions to find a Pareto-efficient set of solutions. First, we start off by creating all combinations of tasks. For example, if there are 3 tasks ABC, there are 5 combinations. A task being alone means we will attempt to swap it through the AMM. A task not being alone means it will be cow matched against other tasks in the matching. From the combinations, we first filter out possible combinations. A possible combination is defined as a combination where all matchings of tasks are ones where the tasks are alone, or all matchings of length greater than 1 have at least 2 tasks that have opposite 0 for 1 value. From the possible combinations, we first filter out feasible combinations. For each matching of length 1 in the combination, we find the output amount quoted by the AMM for the swap. For each matching of length greater than 1, we exchange tokens between 0 for 1 and 1 for 0 tasks and calculate the price at which swaps effectively took place. A combination is then considered feasible if and only if all matchings are of length 1 or all matchings of length greater than 1 are being matched at a price where the users are getting a higher number of tokens than they would have the AMM pool. From the feasible combinations, we find the best combination, where total token 0 and token 1 amount is higher with a bias towards token 1. For example, A and B pool setup such that 1A is equal to approximately 3.999B. 3 tasks are created in a batch. Sell 10A for B, sell 80B for A, sell 20A for B. The operator will find the following to be the best combination. Task 1 got swapped through AMM. Task 2 got cow matched, receiving 28 tokens for 20B tokens, which is 1.1198 tokens more than the AMM. Task 3 got cow matched, receiving 80B tokens for 28 tokens, which is 8.6106B tokens more than the AMM. The biggest challenges of building this project was finding a good matching algorithm. I don't have any formal background, and Cow Solvers is an MEV-like game where the algorithm is only valuable as long as it's closed source. After several hours of research and learning, I learned about Pareto sets and Pareto efficiency. Then through a brute force algorithm and several trial and error iterations, I landed on V1 of the matching algorithm that now exists. To take this project further, there are a couple key points I immediately need to address. The AVS contracts need to enforce a minimum operator weight designed such that operators cannot process a batch that is transferring value larger than their stake. The operator code can be updated to support interpool cow matching, allow accessing sources of liquidity beyond the Uniswap AMM. Now let's have a look at a demo. The anvil node is running, we started our operator, and now we are creating 3 tasks. Task 0 got created with 0 for 1 true and amount specified minus 10. Another task 1 got created with amount specified as minus 20 and 0 for 1 true, and task 2 also got created with 0 for 1 false and amount specified minus 80. Here we should see that task 0 should get swapped through AMM and task 1 and 2 should get cow matched. As you can look through the analysis, task 0 got swapped through the AMM and task 1 and task 2 got cow matched. Thanks a lot everyone, hope you enjoyed our presentation.